Thanks, Lindsay. Thank you all for joining us today. I'm going to discuss our tool steels and how to go about identifying changing tool steels, why it's warranted, and how to select the right steel for your application. As any tool, you'll know all tooling is not created equal. There are many different inputs that contribute to optimizing your uptime. The die design, the tools themselves are important, but just as important as the tool itself would be the materials that's being made out of, the heat treatment process, and any improvements to the finish, surface finish, coatings, and whatnot that you do on top of all that. Since this is about tool steel, we will move forward right away with how to choose your tool steels. Different designs, there's air melt, remelt, high speed, and powder. We'll go through those over the next few slides and then get into the wear differences and heat treatment and why to choose where you can. Tool steel itself is basically a few fundamental characteristics that are most important. That'd be the matrix, or what holds all the alloys together, and the carbides. The carbides are what give you your additional wear resistance and hardness. The matrix is basically the mortar that keeps everything together. It has a lot of chromium and cementite that provide the basic fundamentals for steel, such as your hardness, your basic wear resistance, and your basic toughness, commonly found in your A2s and your D2s. As you add different carbides, they are going to increase the wear resistance, have added hardness, and reduction in toughness. The size and volume of these carbides are also a limiting factor in what makes up the composition of the tool steel, so we'll get into that a little bit further along as well. As you all know, steel making is a fun little process. Commodity steels themselves are all done the same way, heated up, ran through a process called making an ingot, poured into a mold, and then from there it is going to be made into a big giant block of ingot, which will look something very similar to that. Different carbide types that make up those ingots. I can tell you before, your cementite and your chromium carbides are your standard air materials. You get into the molybdenums and the tungstens, we'll get into your M-series steels and your T-series like the T15s. Then your vanadium carbides, typically found in your powdered metals, we'll get into the 3Vs, 10Vs, 15Vs, and so on and so forth. There's a lot of new steels out on the market, so being aware of what's coming out and the different volumes of these carbides will be critical in deciding what to choose. Carbide structure itself is broken down into a couple of different methods of manufacturing, and this is a big proponent on how the tool steel itself performs. Conventional melt carbides, which is shown on the left here, are less uniform and are typically larger in size, and whereas the powdered metal, and I'll show you how that process is done here in a little bit, are much smaller, much more uniform, and provide a more consistency in the tool steel itself. Carbide content and how it's processed is a big factor in what manufacturers will use in the tool steel and how well it performs out in the field. So once you've gotten your ingot made, you're going to run across into some forging, which compresses the material and its contents together under heat to create a bond that will be the strength of that material. And then after it's forged, we'll move along into a rolled out process. The material will get rolled, whether into a flat stock or a round stock. And then from there, it's going to be, if it's a round stock, it's going to be straightened and then ground to a nominal size, sometimes even a precision finish, to provide more consistency for end users. The critical part about the bar itself is you want to have that nominal size and consistency all the way through that bar. When you're sticking it into a lathe and you go to finish up something different and make it a smaller or usable part, if you don't have that consistency, you're going to get some issues with size and then possibly in a damaging tooling and your machine. Another method of manufacturing tool steel would be remelting it. It's actually an interesting way and it's kind of more and more prevalent nowadays. It adds additional stability and improves life to the tool steel itself. By remelting the material, you reduce the amount of impurities and sulfur, creating a higher quality ingot. So then you go back through forging and the rolling process, you're going to have a better bar of steel to begin with. Quite often this is used in aircraft, manufacturers, power plants, and even into military applications. But it is becoming, like I said before, it's becoming more and more relevant in today's commodity tool steels. The other method, more commonly seen is particle material or powder metallurgy. Sorry, had two combined there at the same time. Powder steel is pretty cool. Basically, you come across the powder which is completed by melting the material into a crucible, and then it's passed through a high-pressure gas jet or atomization. This forms the molten material in tiny pellets. That's what you see on the top there, the different forms of the material itself. And then those are sometimes referred to as micro ingots. So those ingots then are encapsulated and ran through a heat process or a hot isostatic pressing. And then from that point, it'll go back into the same method everywhere else, so it'll get forged, rolled, ran through a grinder again for the bar, and continue along that process. Another little tidbit about powder metals here, the sintering process. This is where the dense structure minimizes the inclusions or the voids that are common in the commodity grades, which is where your carbon can get in the way. The carbides themselves are now very small, very uniform, and they adhere better. So when you use that sintering process, they'll get into a solid bond amongst individual carbides, creating a better flow of that material. Now we'll shift our gears here a little bit away from how tool steel is made into why you would want to change to a different tool steel. The most common reason today is performance. As you all know, keeping your machines up and running is very critical, and making sure your uptime is at its optimal level is what the tool steel will help you with here. So some of the biggest concerns with material itself are wear issues based on material adhesion, or breaking due to compression, or just standard wear. Changing tool steels will provide an improvement in your uptime of your machines. How to determine the failure process. The steel typically itself will help you in that analysis. You look for the root cause of the failure and kind of work backwards from there. So if you look at the tool steel itself, it'll show, on the one on the left, there's a catastrophic failure, probably done under compression of some sorts, and the material too brittle, broke away from the application for the rest of the punch. The middle picture has a little A, B, C, and D there. That shows little chipping and then some micro fracturing done in that material. And then you can see the far picture here. You'll see some more inclusions of bigger grains of carbides. Those are causing some breaks in the material. So your first step is to evaluate how the part failed, and then work backwards in the steel properties themselves to improve the process. Now, what I mean by improving your tool steel to be, look at the failure point. As we go along here, we'll kind of point out some of the failure points and how to use different tool steels in those applications. So we'll start here. Depending on the application, your production parameters, and the work material, one or more failure mechanisms can operate at the same time. In blaking operations, actually, all of these failure mechanisms can occur. In forming operations, typically you're going to see your galling, your wear, and your deformation. So let's go through and define each one of these areas a little more specifically. Depending on the application, you're looking at abrasive wear itself. That occurs when a hard surface slides across a softer surface. Basically, ASTM defines that as a loss of material due to hard particles that are forced along a solid surface. Obviously, you guys know what that means. It's just your chip wearing away from your work material. Abrasive wear will always wear away the edge of the tool, resulting in a loss of mass. That loss of mass, you clean up over time. It gets bigger and bigger depending on the amount of wear. You're all aware of that. But ways to reduce that abrasive wear is to change the tool steel, or even the hardness or the carbide content, which would be the tool steel change. Typically speaking, every 2 points of Rockwell gives you about 15 to 20% more wear resistance. Changing your carbide won't give you that same amount of gain, but what the carbide type will do is it'll make it a more stable material. So when you do make those Rockwell point changes into a higher level, the carbide can contain that and not give up some of the other functions. You know, if you were to add A2 and start at 58 to 60 and get some good wear, you can get all the way up to 64 thinking you're going to get 40% more wear resistance. You might get that, but you're going to give up the toughness and the compression strength that A2 offers, and you're probably going to have other issues that come along with that. So that's where you combine the Rockwell increase with the different types of carbides or the different base tool steels, what I'm getting at for that. Galling itself, obviously, is a material adhesion of the work material to the surface. So your work area is sticking on the punch or the die land, and the severity of that galling does depend on the surface finish of your punch and your die, and the chemical composition of the tool steel and the work material. Your aluminums and your galvanized obviously will want to stick a little more than your harder work materials will. Softer materials, well aware that they don't have a good surface finish or a hard surface finish on your punch, you will pick up some more adhesion. This adhesive wear here occurs when the material being formed transfers to the tooling is doing the work. As you see on the left here, the drawing process of the form is picking up material along the radius where it's being drawn or formed, where all that pressure of the material is being put on. Increasing that hardness and machinability of the steel are important. Surface finish obviously is very critical and in the drawing process. So having material that will machine consistently, wear evenly, and polish well are very important. You can see the machine lines in that surface finish of that punch. Being able to polish them out would be a critical aspect of changing your tool steel. So if you were to go to a harder steel, making sure, you know, like a 10V or something like that, making sure you're able to still clean up and machine that properly. So your tooling itself, you're using to do all your manufacturing, your radius, your cutting tools, and your grinding wheels. The surface finish to begin with is critical at that point. So a 10V is a lot harder to machine than say an A2 would be. So keeping that in mind when you do go change steels. We here at Wilson Tool use a lot of different applications for different tool steels. So we kind of have that speeds and speeds. So talk that over amongst your tool steel guys. They'll help you out a little bit. Or you can give us a call here and we'll be able to help you out with a little bit of feed and speed information to help with the machining. And adhesive wear kind of comes across a couple other ways too. You see a micro welding of tool to the work material. And the frictional contact generally refers to unwanted displacement and attach of that wear material to one surface to another. And from that point, you will often see adhesive wear coming across thinking it's abrasive wear because the material is adhering to it for so long and then it fractures away from there and does it, the left side here doesn't kind of pit away from the material and gives you that concept or thought that maybe it was abrasive wear and the part was failing because of the contact, when in all actuality you were getting that micro welding occurring and then eventually the surface became too big and it broke away and pulled some of that substrate material with you. So again, you know, changing the material type, you're going to a higher Rockwell on that, and even coating that punch will help with that. The coatings are a big thing here to help prevent that adhesion as well. The next one here would be a compressive forces. A deformation occurs when material yields under compression, typically due to the force being higher than the yield strength of the material. It also could be due to, more often than not, poor heat treatment processes or being under the optimal Rockwell for the performance range itself. So increasing it to a tool steel that is a higher compressive strength and a higher range of hardness would be recommended. If you're getting some bending in a F7 under that compressive strength, even changing that Rockwell a couple points will help. You're obviously going to lose some of that toughness, but the compression strength of S7 will be pretty good. So if you're seeing that in an M2, verify your Rockwell process, making sure your hardness has been is in that 60 to 63 range. If it's less than that, verify the draw temperatures and everything else, how that was taken care of. So the thing you want to watch out for though when you do change your compressive strength is you're not impeding on the tensile strength of the material, and then you're going to, if you do that, you'll change from a deformation into a cracking or a chipping, which would be the next problem that could occur. So let's take a look at that chipping and cracking. Chipping and cracking is really a result of the tensile strength and passing the threshold of the material itself. So the forces that are putting on there are far greater than the tensile strength of the material. Other than hitting something that was not expecting, unexpected, like a slug being pulled or something like that. Cracking typically occurs when the tension force exceeds that tensile strength of the material. Typically it's seen from impurities such as the sulfur or the carbon, or even a carbide chunk on the areas that chip away first. Cracking is just a bigger area that cannot hold that surface. So you might see a small chip here and there, or you might see a big crack, and that big crack is the same way as the chip is, just a bigger area that broke away. Two basic types of tension failures, kind of show the drawings down below. On the right there, the ductile or the brittle failures. Now, ductile failure really is slow acting. They both have their pros and their cons. The slow acting ductile forms, they show signs along the way. You might see some changes in your product itself before it breaks away. But then again, you might not see that. It's kind of the con. You know, you're going to see small, minor changes in that. Because deformation slowly building up. Eventually, in a tighter tolerance product, you'll start throwing away scrap because of that deformation, and you're not going to be able to see it right away. You have to go back and find the punch and realize that it's expanded a little bit on the cut edge, or a little bit below that quite often. Brittle failure itself is a clean cut. There's no warning whatsoever. It breaks. I mean, you don't see the crack happening ahead of time. You don't see it in your finished product because it's not changing sizes, and it snaps away. You've all seen that at one point or another, and typically speaking, that's your catastrophic failure, where you end up seeing that down the line a little more. Sometimes you have safety features built in where that brittle failure is what you want to see, and if that's the case, going to a higher steel, like a 10B, a little more wear resistant, but not high in the toughness and the compressive strength, that 10B would be a way to go for that. If you are looking for more of a ductile response, you know, an S7 or a A2 gives you that opportunity. Your M2s and your other powdered M4s and molybdenum kind of base materials see a little bit of that as well. But when you add more vanadium and get a higher Rockwell into that T15, 10B range, carbide obviously does that, which is a benefit for that is it breaks. Your safety features will catch that. So depending on how your dies are designed, keep in mind you want to make sure your materials will follow that process as well. So again, chipping, you see on the edges there, I have two different pictures here. One's under a 200, 300 times a view. They're just chunks of carbide or inert material that is breaking away from the edges. Typically speaking, it's just because the tensile failure the pressure's exceeded that, and it has to find the weakest point. And those weak points, if in the standard air melt materials, will be a little more prevalent than they would be in a powdered metal. Powdered metals typically will have less of that inert material in there, less problems happening along the way. So you'll see a little less of that chipping and more wear occurring in that aspect. So our first question of the day here is, what is your most common tool failure? We'll give it a moment here. Be able just to answer one of those along the way. Lindsay will take care of that here in a second. All right, I think the poll should be out there. This tells me you're all hearing me, at least I can see the poll results coming in a little bit, so I know I'm not talking to air here. I guess that's a good thing. I always wonder if I'm talking to myself sometimes, but. All right, looks like everyone is just about in here. All right. So looking at the results here, looks like the majority of you guys see wear, 36% chipping, and then galling is kind of the next big issue. So wear and the chipping, obviously that goes back into the types of steel you're running. So when you're running into a wear issue, typically speaking, you're running with a cold work steel to begin with a lot of times. I hope you move on from that into your M series materials, at least into the M2, which would be in your high-speed steels. These typically run with a little more carbide content, the chromium, the tungsten, the moly, the vanadium, and cobalt. Those are what are going to give you your prevention for wear. and your chipping a little bit here. Into the powdered steels themselves, the best combination of compressive strength and wear resistance is what a powdered steel kind of offers you. Again, we talked about a little bit in the manufacturing process that the material itself, smaller particles, a little more close-knit. You can get the material, the carbides to bond better together, giving you a higher compressive strength and more wear resistance. Depending on the application, a variety of options will exist. In toughness, strength areas, you run a 3V, it's a good option, but it's not a very good option for wear resistance. Again, that'd be going into a 10V, or a powdered metal M4 is kind of a best of both worlds, or our Ultima M4 would be an even higher compressive strength with more wear resistance, kind of a middle ground between a 3V and a 10V. A quick little chart here for you all to take a look at. You can see the differences when you give up one thing for the next. So always keep that in mind. These are available. I can send them out, or you guys can probably find them pretty easily online. Where toughness, you get into that air material, your H13s, your A2s, S7s. You add into some more powder, you can vary your carbide content to give yourself more wear resistance, more compressive strength, or more toughness, depending on how you want to do that. So there are new materials being developed all the time. Wilson Tool works with a lot of different tool steel manufacturers and mills to develop more application-specific materials when we see something happening. That's where our Ultima M4 came from, collaboration with a mill to develop something that would give us a little more wear resistance and along with that toughness. So I know we're running a little long on time here, so I'll try to fly through these heat treating process pretty quickly. It is a very important process and very important to the tool steel itself. They're done very different methods a lot of times. Controls a lot of different atmospheres or bars in an oven. A lot of 2-bar ovens, a lot of 6-bar ovens, which is what we here at Wilson Tool use. The more bars you have, the better the stability. It's basically atmospheres in a vacuum chamber. You get a better stability, higher capabilities of running the material in different ranges, and more consistency. So you want to get your material to the optimal hardness to begin with, which is your Rockwell, and then from there you're gonna temper or draw that back down into a performance Rockwell. That way you can get into whether it's going to be into a higher 62 to 64 range in your 10Vs and your M4s to get some good wear resistance, or maybe even into that 58, 60 in your 3V range materials to get that better toughness. So you got to vary different temperatures, and you want to make sure your tool steel providers, or if you're doing this in-house and sending it out, that your metal treaters are ones working towards optimal performance and not batching this with a bunch of other stuff. When you batch materials, you have a big effect on the process itself. Tempering itself, and that's usually when you see these big changes, is during the tempering process. This here is an example of A8, where it does change pretty quickly depending on that process. So making sure you're working with, if you're not buying a finished product from someone, if you're sending out your material, making sure you're working with that metal, your heat treaters to get that optimal range and not batch it in with other materials that are widely different and have different draw times. So that will cause some dramatic changes in your material. It may not show up because you're still going to see that Rockwell number there, but the toughness might go away, or you might see the toughness but lose that Rockwell number. So you kind of got to keep an eye on that. I'm going to bypass the question number 2 here because we're running a little out of time. My point behind this question really was get to know your heat treater, whether it's Wilson Tool manufacturing the product for you, understand what we do. We do everything in-house. We run it through set group of products to make sure we control the environment in which it's being heat treated in and then drawn back on. You want to make sure that if you're not buying product complete, you're sending it out to heat treaters, consult with them, get to know your heat treater, get to know your tool steel guys, talk to them about the optimal performance of those materials. They're more than willing to sell you just about anything, and I think we probably are as well. But getting to understand that is a big difference, and I think that's why we're here to tell you that heat treatment of material makes a big difference, only in the fact that it provides you that hardness and that toughness of that product. Any changes in your heat treatment can just take away anything you've done in your tool steel changes. You might be having wear resistance or running M2, and you went to a 10V, but it was not drawn properly. Next thing you know, you're getting less wear resistance, and you're seeing problems all over the place. You're getting chipping, and you think it's because it's too soft. You make it harder, but it's just a draw temperature issue, or it's been set, didn't dwell long enough at temp in the vacuum furnace, or the quench time was too slow or too quick. It is very critical to make sure you follow those processes as recommended by the providers. So this is a standard chart, just right out of Crucible's former books, taking a look at the typical hardness. They have a range, and each one of these will have a catalog page. Typically, tool steel providers, you've probably seen, they'll give you some heat treatment requirements or maybe some messages on how to do that. Maybe the best way to go. So I think from that, let's hear a little bit on toughness, and then we'll finish up with some wear resistance. The toughness itself, you see a wide variety of materials here. If you're looking just for toughness, your Venetia is 4 extra or 3V. There's new stuff out by Bowler, 8V, which is very tough material. S7 is probably the toughest at 57 Rockwell, but each one of them have a give and a take between toughness and wear resistance. The wear resistance itself can get pretty steep in changes. You saw the F7 on the previous slide. You get all the way to that 10V, which has got some very high wear resistance. If you notice, the 8V in this case here is pretty high in the wear resistance as well. So take a look at what you're looking for. If you need that wear resistance, the 10V might be the way to go. If you're looking for toughness, the F7 might be the way to go. In the middle, you'll see the Venetia 4 extras, the PMM4s, the T15s, 10, and the 8V kind of give you a good range of both. So make sure when you're looking at that, you might see a material that your material itself is a major factor. So whatever your work material is, would kind of help you decide where to go. You might think you're seeing a wear issue though. Make sure you're not just passing it off as a wear issue. Especially like in stainless steel, you see a lot of wear concerns where you think that going to a harder material would be the way to go. So we switch to a 10V, let's say, because that's going to give you more wear resistance. But typically speaking, actually, when you run a stainless steel with a tight application, you're actually getting a microchipping. Like we had mentioned earlier, the material itself wanting to fatigue and break away on those edges because the tensile strength is just not there. So that toughness comes into play. So actually going to a 3V where you're giving up a lot of that wear resistance, which 3V is more on that Venetia 4 extra range, you'd see some tremendous gains in the toughness, and the wear resistance is still okay. But then combine that with the coatings. Never forget the other options you have available besides tool steels. Coatings are always a big ploy in that. And surface finish, changing the direction of the grind of the punch, adding a polish to it in a galling issue, that might help out in that process. So tool steel is one major avenue for that, but make sure you combine that with whatever other options that you're seeing. Don't just limit it to the tool steel, or just add coatings to an M2 so you can get wear resistance when it might not be the right material to begin with. So, and I'll leave you with one last chart here, and then a quick Q&A. If you have any questions, please send them in. This chart here shows a kind of a change from the commodity grades, which will be the little circles all on the left there, to the powdered steels, which typically drift off to the wear resistance on the right. In this business, the combination of wear resistance and toughness are definitely needed. You all are aware of maintaining that balance between keeping your die running and cost. So A2 has, obviously been widely used over the last 40 years because it's a relatively tough material with some decent wear resistance, and it's very inexpensive. But as you get further along, each one, like I said, a couple points here in Rockwell is 20% gains in wear resistance. As you move further and further on this chart, that wear resistance gets pretty strong, and you're not giving up a lot. So keep that in mind when you balance that out. Look at the cost and just determine really what helps you out in the end. For that, if it's a quick job, you're doing 1,000 pieces, 10,000 pieces, or something like that, A2 might just be sufficient, or an M2. But when you get in those long-running jobs, your Ultima M4s, your PM4s, even your 10V, where you're not having any toughness issues whatsoever, would be the route to go. So There's a balancing act. Go ahead and, you know, give us a call, talk to your tool steel providers, and see what is needed. So with that, I just want to say thank you for taking your time. I know I went a little long here, but let's see if you have any last minute questions. We can see if I can address those for you.